Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so hi, Luca. So this is going to be a talk about logic types, concurrency, and non-determinism, a pretty vague title. So, but namely, I will essentially focus on an approach to integrate non-determinism into a carry-hour interpretation for session type, so to speak. So I will start also with a citation from Typeful Programming and with a picture. And we can see there, Lucas says already in the introduction, we can say that Typeful Programming is just a special case of program of specification. And one can, of course, read type as a synonym for specification and type checking as a synonym for verification. This view fits well with the typeless proposition paradigm of axiomatic semantics and the proposition as types paradigm of intuitionistic logic. So, of course, everyone knows how fruitful and successful has been this idea of carry-hour in the context of functional programming. Although, also I think everyone knows that it is not so easy to see how to extend this paradigm towards concurrent programming in the sense that, for example, in this classical case, you have this correspondence between these really two independently defined things, let's say, lambda calculus on one side and intuitionistic logic on the other side. So, in fact, on the other hand, recently, we have developed with Pfennig and others this new interpretation of linear logic as a very natural session type system for an independently defined programming language, which is essentially the pi calculus with the session types. With session type, this is a typing discipline in which you can define protocols according to which processes nicely interact with each other. So some of this work, of course, is inspired in some work we did with Luca 10 years ago or something on substructural logics for concurrency. But of course, it's a different spin-off. So some key highlights about this type system. One is that one gets, this is a very natural session type discipline, ensuring deadlock freedom and session fidelity by these purely logical means. Proof convergence actually turns out to express laws of observational equivalence. Proof reduction matches process full internal reduction, and is actually also confluent and terminating. And we can compute a normal form of a process which essentially defines its behavior with the external environment. So it is also true that in the very same paper, a few paragraphs below, Lucas says that we can also extrapolate this correspondence and turn it into a predictive tool. If a concept is present in type theory but absent in programming, or vice versa, it can be very fruitful into both areas to investigate and see what the corresponding concept might be in the other context. So what about non-determinism? Okay, so it turns out that non-determinism seems to resist this reasonable analysis in terms of a carry-hour correspondence, essentially because proof reduction must be compatible with if proofs are to represent processes, should be compatible with the process reduction. And since proof reduction should be compatible with proof identity, then it should be compatible with behavioral equivalence. So it does not make much sense to think about a non-deterministic notion of reduction to start with. So in this talk, I will sketch a possible turnaround to this issue in a purely logical-based way. So let me just briefly overview the type structure of these linear logical motivated session types. So the idea is to understand the several linear logic connectives as protocol descriptions. So for example, the tensors denotes the protocol that starts by sending a session of type A and continues with a session of type B, and the par denotes a session that starts by receiving a session of type A and then continues as a session of type B. So those familiar with session types can easily recognize here the familiar type structure of session types. By the way, I'm based this current presentation in classical linear logic with a rule of mix. So there is a natural duality on session types which mirrors the two partners, which flip-flops the protocol in which two matching partners of a protocol are involved, and which essentially correspond to linear logic negation. The form of our typing judgments are pretty standard. So we have a process and two contexts, typically a linear context and the Cartesian context. So the linear context registers the types of the open sessions, and the Cartesian context registers the types of shared servers, which are replicated entities in the environment. Okay, very well. So let me just show you a couple of typing rules. Cannot go into detail into them, but they are pretty natural. So starting for the composition rules, so the parallel composition are represented respectively by the rules of cut and mix. So cut represents dependent communication. So process P and Q communicate through channel X, which exhibit matching protocols. So you can just plug them together and hide the communication channel. And we can also compose processes independently by the rule of mix in such a way that there will be no communication between the involving processes. For send and receive, we can see that the tensor is interpreted by the output process, and the input is interpreted by the par in a more or less expected way. What is interesting in this interpretation is that if you look to the principal cut reductions applying to the several proof rules, you can essentially recover the standard reduction rules from the pi calculus. So here we retrieve the communication rule, and if you look to to other rules, as for example the typing rules for termination, for inaction, and if you look to the principal cut reduction, in this case we essentially retrieve a structural congruence, which means erasing the unit from the composition. And if you go on and look, for example, for the rules for the additives, which in this case correspond to the plus and with connectives of linear logic, you then essentially retrieve the reduction rules for in this case, for anonymous choice. Of course, you could extend this to labeled choice, to labeled sums in the expected way, just for the sake of readability of a program. So this is a very simple example. I can go through in detail over it. Essentially, there is this composition of two systems, a server body and a client, Alice. The server body offers movies, and it offers two options. Either the user sends a title and a credit card and gets back the movie, or it just sends a title and gets back the trailer. So in this case, Alice asks for seeing the trailer of Solaris. So these protocols can be typed by these linear logic formulae, and you get a typing derivation for the full system, ensuring that the system works well, is deadlock-free, and protocols are followed. Okay, so about non-determinism. So our idea of introducing non-determinism essentially is based on these two ingredients. So you actually introduce this kind of a choice process, but this choice process will essentially represent the superposed alternative states of the computation. So you will never actually reduce this process to any of its components during reduction, unless in certain situations. So, and moreover, they can essentially proliferate. So during a computation, you can get further alternatives, or at some points in computation, you can observe alternative states because they are essentially the same. For example, this rule which expresses idempotency of behavior of sum with respect to dissimilarity turns out to also to be derivable in our framework in terms of a proof conversion. So this is one part of it. The second part of it is at the level of types. And what we do at the level of types is to be typeful, we introduce two new dual connectives to express non-determinism. So essentially, these are kind of monadic operators. One which express the type of sessions that might produce any session of type A. This is a kind of a power construction, if you want. And the dual type, so these are classical things. So this is a dual type, which is a type of session that may consume one of those non-deterministic sessions. In our system, we have this, also this kind of natural duality. So it could be interesting to look at typing rules briefly. So I cannot go into details about how these rules have come out. So there is lots of engineering of inference rules going on here, I guess. But you can look to the paper to see more in detail. But essentially, we have a proof rule to introduce a non-deterministic type from a deterministic one, so basic injection of the singleton. So we have a rule to combine non-deterministic behaviors through this alternative process, which essentially corresponds to flattening of the power set domain, so if you want, just as an analogy. And a rule for promotion of the co-non-determinism, which allows us to plug any arbitrary non-deterministic behavior from the outside through cut if everything in the context is already non-deterministic. Okay? So what can we say about this rule? So we can extract some reductions from this. And the basic reduction corresponds to promoting a non-deterministic type to a deterministic one once you get the basic introduction rule and you get to a deterministic thing. Okay, so this is easy. And this one is more interesting and essentially is mapped at the level of the process calculate, not in a reduction, but in an equation. So in a kind of structural congruence. And it essentially allows us to propagate, as you see here. So we have a process P in parallel with an overlapped state. So the cut reduction, what it does is just to propagate the P towards the both side of the alternative space of possibilities. So essentially, it turns out this roughly corresponds to the distribution of parallel composition of a choice, so a well-known behavioral equivalence in the world of process calculi. Okay, very well. So we can get out some basic laws. So these kind of principles are derivable in our system, and they can be realizable by specific typing process. So just for a very, very simple example, I'm about to conclude. So this is essentially an extension of my previous example, but now we have this who identity, which could non-deterministically behave like Alex or like Bob. And Alex is like before, he wants to see a preview of Solaris, but Bob actually wants to buy Inception. So you can compose the system, and the system now gets these types. So for example, in this case, it is very simple to type the who process just by giving it a non-deterministic type of the same bus type as before. As far as the body of the server is concerned, which is not depicted here, but we can try to recover it from the previous slide, you type it with a co-deterministic type, which is possible to introduce here because the rest of the context is empty. If in the case there were any other open names here involved in the definition of the behavior of the body, they should be also given a non-deterministic type so that the system is kept sound. So very, very briefly, just to terminate what kind of results you get. So you get cut elimination holding, so the system is sound in some sense. From a practical viewpoint, you get that our L-type process don't go wrong, so they are deadlock-free, confluent and terminating. Can show that using a pretty standard logical relations kind of argument. And you also have that reduction, so internal reduction actually preserves observational equivalence because non-determinism is essentially represented by keeping open all the space of possibilities. Well, pretty much like in a quantum state in the quantum mechanics. Finally, it is interesting to see what if you just add to our operational semantics the typical collapsing rules of internal choice. And what it turns out is that if you do that, you obtain this kind of interesting postponing result, which says that if a process reduces to a thing of this form, so a choice of prime components, so a prime is something which is not trivial internal choice itself. Then, of course, using the extended reduction rule, you can obtain the corresponding reduction to a particular collapsed state. Okay, of course, you can do that just by, this is the easy part. You can do that just by applying these rules at the very end of the reduction. But on the other hand, you also have the converge. So if we pick up the set of all processes, of all prime processes to which a given initial process reduces, okay, then this set is actually, in our case, this is finite up to structural congruence. And it is possible to, in the original system, without collapse, to produce a reduction to a state that represents the whole set of possibilities. Okay? So this is essentially what I would like to show you. This is a gift I would like to offer Luca for the occasion of his 6th decade. So thank you.